Okay, so starting chapter 4 is all about probability. And before we get into calculating different probabilities, I want to introduce you guys to one of the main concepts behind statistics. And that is, what does it mean for something to be statistically significant? In the following chapters, as we learn even more about the normal curve and other distributions, we want to be able to prove whether or not something is statistically significant. So let's kind of get like a gut feeling for what that is. So a set of measurements or observations is said to be statistically significant if it's unlikely to have occurred by chance. Like it didn't happen on accident. It wasn't a fluke, okay? So let's look at these two examples and determine whether or not they're statistically significant. So let's talk about the global average temperature. The 15 years from 2001 to 2015 were 15 of the 16 hottest years on record up to 2015, using records that go back to the 1880s. Okay? Now, would you say that having 15 of the 16 hottest years on record occur in a single 15-year period is statistically significant? Yes. Yes, this is statistically significant, right? This didn't just happen by chance. Now, in the second example, we have the team with the worst win-loss record in basketball wins one game against the defending champions. Is that one win statistically significant? No, right? It's likely to have occurred by chance. Okay, so this is not statistically significant. Even bad teams have a good day sometimes. So what if a researcher conducts a double-blind study that tests whether a new herbal formula is effective in preventing colds, okay? So during a 3-month period, 100 people take the herbal supplement and 100 people take the placebo. So in our guts, think about how many people out of those 100 would you expect to get the flu? So they studied it and their results were 30 people in the treatment group got colds while 32 people in the control group got colds. So the control group didn't take the supplement, the treatment group did. So do we think that this herbal formula is effective in preventing colds? No, 30 and 32 are too close together. What number would this need to be for you to feel like it was statistically significant? Maybe 15? That's half of the control group. So 50% more effective at preventing the common colds. I might take it, right? What about if it was 5? What about if it was 1? So think about how it'd be more statistically significant as the number of people in the treatment group who got colds went down. Now, when we talk about statistical significance, we can quantify it, okay? And in general, we determine whether something is statistically significant by using probability to quantify the likelihood of whether something happened by chance. Okay? We might have to ask a question like this. 1. Is the probability that an event occurred by chance less than or equal to 0.05, which is, by the way, 1 out of 20? Right? That's pretty statistically significant. 1 in 20 likelihood of occurring by chance, less than 1 in 20. So how do you determine if a result is statistically significant? So if the probability of the event that we're going to calculate occurred by chance is less than or equal to 0.05, we say the event is statistically significant. And if the probability that the event occurred by chance is greater than 0.05, we say it's not statistically significant at the 0.05 level. We can also do that at the 0.01 level. Only use 0.05 and 0.01, right? Anything bigger than that is not statistically significant. If it was 1 in 10, so 0.10, right? That doesn't feel statistically significant, right? We need better odds. So, in the test of the polio vaccine, only 33 of the 200,000 children who got the vaccine got polio, while 115 of the control group got polio. Okay, so they did a precise calculation, which we're going to learn how to do in a later chapter, and found the probability of this occurring by chance was 0.0000, so many zeros too. Was this result statistically significant? Yes, this was a statistically significant result, right? And it was because this number is so much less than 0.05 or 0.01, right? So it's statistically significant at the 0.01 significance level. Okay, so let's keep talking about probabilities. So let's talk about the differences in probability and statistics. So in probability, what we do is we make a conclusion about a sample based on our knowledge of a population. Okay, population means we know everything in the sample. In statistics, we make a conclusion about our population based on the knowledge of our sample. Okay, so it's a little bit different. One goes from sample to population, the other goes from population to sample. So let's say we know that 1 out of 10 students at Fontbonne live in the dorm, and then if we take a sample of 50 students, we will probably get about 5 dorm students. So here we're taking information from our population and pushing it down to our sample. If we were doing this statistically, if we took a sample of 25 students and found out that 10 of them were athletes, we could infer or guess, right? We're talking about inferential statistics, that 10 out of 25 or 2 out of 5, 40% of students would be athletes. So we're taking information we collected from a sample and using that to assume something about our population. So an introduction to probability. So we need to start with 5 definitions: procedure, outcome, event, simple event, and sample space. And those are going to be really important as we come to learn how to calculate different probabilities. So, a procedure is any process that allows us to obtain observations, take measurements, collect data, things like that. So it could be rolling a die, it could be flipping a coin, it could be measuring the temperature, right? So it's any process that allows us to collect data. An event is any collection of outcomes for a procedure. So we use letters to denote an event. So let's say our procedure was that we're going to flip a coin. And then the 2 events that could come from that are heads and tails. A simple event is an event consisting of exactly 1 outcome. So an event is any collection of possible outcomes, and a simple event is just 1. So that could be just heads. The sample space is all possible simple events. So that'd be heads and tails. That's the only thing that can happen when you flip a coin. So notational wise, we denote P to be probability and ABC specific events. So P of A denotes the probability of event A. So if I had my process was to flip a coin, I could get heads or tails. So then the probability of heads would be the probability of heads happening, and the probability of tails would be the probability of getting tails. Now, I'm sure you might know, when you flip a coin, the odds of getting heads is about 50%, and the odds of getting tails is 50%. But where does that information come from? Well, we're going to find out today. Last key point about probability is a probability can only be between 0 and 1. 0 means it's never going to happen. 1 means it's absolutely certain. Okay? You're never going to have a probability greater than 1 or less than 0. Okay? So the closer the value gets to 1, the more likely it is to occur. So symbolically, we write that P of A, so the probability of an event, is always 0 is less than or equal to the probability of A, which is less than or equal to, I want to write it like that, 1. So let's consider tossing 3 coins. And we'll label the coins, coin 1, coin 2, and coin 3, so we can track them. The sample outcome of this space consists of 8 possible outcomes, right? So first one could get heads, heads, heads. Then I could get heads, heads, tails, heads, tails, heads, and so on and so forth. So there's 8 possible outcomes. Some simple events are tail, tail, tail. That only occurs once. But some events would be 2 heads land face up. So that would be, here I have 2, here I have 2, and here I have 2. So that's not a simple event because it occurs multiple times. It might be helpful to use a tree diagram to determine your sample space. So here we're tossing 3 coins. Your first 2 options are heads or tails. After tails, you flip your second coin, you could get heads or tails. After your second coin, you flip your third coin, and you could get heads or tails. So if you follow each path down the tree, you get all 8 possible outcomes. So here's head, head, head. This one is head, head, tail. Here we have head, tail, head. Here we have head, tail, tail. Here we have tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. This is just a way to make sure you get all possible events in your sample space. Now, there are 3 different approaches to probability. Classical probability and relative frequency probability. The third one's a little more subjective. We aren't going to cover it that much. Classical is the one everyone's probably the most familiar with, and we're going to learn how to compare these two. So, the probability when it comes to, oops, let me get everybody on here. So let's compare these 3 different types of probability. So classical probability is for simple experiments. That's equally likely events. Like it's used in gauges of chance, and probabilities are exact answers. So that's like the hypothetical of getting ahead when you flip a coin is 50%. But if I was to flip a coin 100 times, I might not get 50%. I might get that there was 48% chance of getting heads. And that's when we have a relative frequency. So you could do it with coins, but typically it's with things that are more complicated. Sometimes all the events aren't equally likely, and this is used the most often. Subjective is the probability of an event A is found just by guessing or estimating its value based on the knowledge of relevant circumstances. The best example I can think of that is when you open your phone in the morning and it's like, oh, there's a 20% chance of rain. There's a lot of science behind it, but I'm pretty sure that's subjective. And for relative frequency, probabilities are only estimates, while with classical, they're exact answers. So for classical probabilities, you put, given the event A, the probability of A is the number of ways A can occur out of the number of events in the sample space. So how many outcomes are there if you roll 2 fair die? Remember, a die has 6 sides, okay? So you can get a 1 and a 1, a 1 and a 2, a 1 and a 3. If you remember counting problems in algebra, this would give us 36. So there's 36 possible outcomes if you roll 2 fair die, and there are tables of these outcomes out there. So what's the probability of rolling 2 snake eyes when 2 fair dice are rolled? So I'm rolling 2 die and I get a 1 and a 1. How many times can that occur in my entire sample space? Well, that can only occur once. 36. So my probability of this event occurring is 1 out of 36. What's the probability of rolling a 2 and a 3? So I've got die 1 and die 2. If I roll a 2 on die 1, I could roll a 3 on die 2. If I roll a 3 on die 1, I could roll a 2 on die 2. And those are the only 2 options. So that's actually the probability of this event is 2 out of 36, which is 1 out of 18. And you can convert those to a decimal if you want. I'm just I like my fractions. Next, what's the probability of rolling doubles? So that'd be getting a 1 and a 1, a 2 and a 2, a 3 and a 3, a 4 and a 4, 5 and a 5, and a 6 and a 6. So that's how many different simple events? 1, 2, 3, 4, 5, 6. So that'd be 6 out of 36, which is 1/6, which is 1.6 bar. Thank you. So let's go through an example. So what's the probability that a randomly selected family with 3 children has 2 girls and 1 boy? Okay? And we're going to assume that the births of boys and girls are equally likely. So let's make a tree diagram. And I'm going to use B for boy and G for girl. Okay? So I've got, you have a boy or you have a girl. So that's your first child. Then we want them to have a second, Then we want them to have a second child, so they could have a boy or a girl. Or a boy or a girl. Then again, they have their third child. They could have a boy or a girl. And I want to know what's the probability that they have 2 girls and 1 boy. So why don't I go ahead and circle the ones with 2 girls. So this first one we can see BBB, only no girls, BBG, no girls. Here's my first 2 girls. I got BGB, that's 1. I have GBG, and I have GGB. So the probability of having 2 girls and 1 boy is 3 out of 8. To compute a relative frequency procedure, you want to conduct the event a large number of times and see how many times the event actually occurs. And based on those observations, we can calculate the probability of an event. That will be an estimate. So what we're doing here is counting the number of times we did our experiment and the number of times A happened. So, for example, geological records indicate that a river has crested above a particular flood level 4 times in the past 2,000 years. What's the relative frequency probability that the river will crest above the high flood level next year? So we're taking the number of, so this is for flooding, we're taking the number of times we've conducted the experiment. In this case, the experiment was every year seeing if this floodplain flooded. And how many times did it flood? We're wondering the probability of a flood, and it says 4 times. So we have 4 out of 2,000, which is 1 out of 500. Or you could write it as a decimal.